Hi everyone, in this video I'm gonna explain how to solve this problem. Um, Essentially we're gonna learn how to deal with the measure of AI. So how to change the measure of a set in this integral of the indicator function of the AIs. And also we're gonna use the maybe something like counting measure to solve the part 1, and part 2 is easier. So we have a measure space and we have some measurable sets. In part 1, suppose every x belongs to at most C sets AI. C is finite. Then the summation of the measure of AIs is smaller than or is no bigger than C times the measure of the union of those AIs. So what's the part 1 essentially saying is as we know nothing about those AIs, we don't know if they overlap or they don't, or how much of their overlap. And we can only know they are measurable, which gives us like nothing about their intersection or something. Then if we don't know if the sets are overlapped, the summation of the measure of each set would essentially have some so we essentially would double count some of the overlaps of those two sets. But if we do know that each x belongs to at most C finite sets of AI, then we can control the double count by timing a constant C. So that's the essentially what the problems are saying. In order to deal with the measure of AI, we can use, so remember the measure of AI is essentially the indicator function of AI, the mu, the integral of the indicator function. So the summation of those mu AIs would just be the summation of each indicator function. And notice here we're gonna use the condition that every x belongs to at most C times of AIs. So maybe this color is weird. Yeah, we can use that one. Oh, that one is also weird. So yeah, anyways. So now we're gonna invoke the counting measure by saying that so essentially we're count so let's say we fix x, and this expression is basically counts how many times x belongs to each AI, which is by the assumption is at most C, right? So here we can kind of notice how that would help us to connect to get the inequality. So then if we change the x, or if we go through the whole space, which is essentially the measure of the mu AI, because we're integrate over the whole space x. So as each x is no bigger than C, we know that the summation of all the x is gonna be no bigger than c times the measure of the union of AI. That's how we could conceptually understand the inequality at the moment. So now we're going to show the details of the proof. So we have that, and let me write the this part. So the union of AI, the measure of the union of AI is essentially the indicator function of AIs. Now let's also do the same thing by fix x and see what the function would do. So basically, if we fix x as as our indicator function is the union of AI, so if x belongs to any of the AI, if x belongs to one of the AIs, then the value would be 1. And if x doesn't belong to any of the AIs, then the value would be 0. So we can notice, or we can get a sense at the time that if we raise it into some like c times of the indicator function, then we can easily get the inequality. So we do the same thing by writing this. Let me just copy paste this thing. No. Yeah, maybe this is essentially we can write it in this way, which is conceptually more clear to me. As we know, we're gonna know clearly that the function value, the function input would be x, and this one just counts if x, or just telling us if x belongs to the union of the AI. So we can argue by point-wise. So as the first part, we show that for a fixed x, this fixed x, this AIX, summation of the AIX is smaller than the C, right? And if it belongs to any of the AI, so which would give us the it belongs to the union of the AI, so essentially we get the summation of those indicator functions is no bigger than C times the indicator function over the union for 1x. Then we can argue that as it holds for a fixed x, then it must hold for every x. So then we get the inequality by taking the limit, or by letting I goes to 0. And for part 2, yeah, maybe I'll make another video to explain part 2. So let's just stop at here.